Welcome, everyone. Today, we are going to explore an exciting topic, matter in our surroundings. In this presentation, we will learn about the different forms of matter, how scientists classify them, and the physical nature of matter itself. We'll also see some interesting activities to understand whether matter is continuous or made up of particles. So, let's get started and discover the fascinating world of matter all around us. Let's look at some interesting experiments to understand the nature of particles of matter. First, take about 10 ml of this solution and pour it into 90 ml of clear water. Then, repeat the process by taking another 10 ml and adding it to fresh 90 ml of water. Keep diluting the solution like this 5 to 8 times. Now, ask yourself, is the water still colored? This helps us see how the color spreads out as we dilute the solution. Next, we move to activity 1.3. Put an unlit incense stick in a corner of the classroom. How close do you need to go to smell it? Now light the incense. What do you notice? Do you smell it even from a distance? Record your observations. This activity shows how the smell, which is a kind of particle, spreads through the air. In activity 1.4, take 2 glasses filled with water. Carefully add a drop of blue or red ink along the side of the first glass and a drop of honey into the second. Leave them undisturbed at room temperature. What do you observe immediately after adding the ink? And immediately after adding honey? How long does it take for the ink to evenly spread throughout the water? This demonstrates how particles move and spread out over time. Moving to activity 1.5, drop a crystal of copper sulfate or potassium permanganate into hot water in one glass and cold water in another. Don't stir, just let the crystals settle at the bottom. What do you see just above the solid crystal? As time passes, what changes do you observe? This tells us about how particles of solids and liquids behave and how temperature affects their mixing rate. From all these activities, we learn that even after dilution or over time, the particles are still present in the solution. For example, a tiny amount of potassium permanganate can color a large volume of water, which suggests there are millions of tiny particles in just one crystal. These particles divide into even smaller particles, explaining how a small crystal can influence such a large amount of water. We can also do a similar experiment with Dettol instead of potassium permanganate. The smell can be detected even after repeated dilution, which again shows how tiny and numerous these particles are. This brings us to a key point. Particles of matter are extremely small, beyond our imagination. They are so tiny that they are always moving and spreading out, which is why we see phenomena like color spreading, smell traveling, or solids dissolving. Now, let's consider the space between particles. In activities 1.1 and 1.2, we saw that particles of sugar, salt, Dettol, or potassium permanganate get evenly distributed in water. Similarly, when we make tea, coffee, or lemonade, particles of different substances fill the spaces between each other. This shows that there is enough space between particles of matter for them to move and spread out freely. Let's explore matter in our surroundings. Now, imagine each student as a tiny particle of matter. The question is, in which group do these particles hold each other with the maximum force? Think about that for a moment. Next, we have activity 1.7. Take an iron nail, a piece of chalk, and a rubber band. Try to break them using a hammer, cut them, or stretch them. Which of these 3 substances do you think has particles held together with the greatest force? Moving on to activity 1.8, take some water in a container and try to cut the surface of the water with your fingers. Were you able to do it? If not, what do you think is the reason behind the surface of water staying together? All these activities, 1.6, 1.7, and 1.8, show us that particles of matter have forces acting between them. These forces keep the particles together. And importantly, the strength of this force of attraction isn't the same for all types of matter. It varies from one kind to another. Now let's consider some questions. For example, why does the smell of hot, sizzling food reach us from a distance, while cold food's aroma only reaches us when we're close? This is related to how particles move and spread in the air. Here's another interesting observation. A diver can cut through water in a swimming pool. What property of matter does this demonstrate? Let's also think about the characteristics of particles in matter. Particles are always moving, which we call possessing kinetic energy. As the temperature increases, they move faster, meaning their kinetic energy increases too. In fact, when we heat matter, diffusion, the process where particles intermingle on their own, happens faster. Why does that happen? Because higher temperatures give particles more energy, making it easier for them to move into spaces between other particles. Finally, Activity 1.6 helps us understand how particles attract each other. Imagine making human chains in different ways, one holding on tightly, another holding hands, and a third just touching with fingertips. Then, a group runs around trying to break these chains into smaller parts. Which chain was easiest to break? Why do you think that is? All of this ties back to the idea that particles of matter are always interacting, attracting, and moving, and these forces and behaviors vary depending on the type of matter we're looking at. Let's observe the different types of matter around us and ask ourselves, what are its different states? We can see that matter exists mainly in three states: solid, liquid, and gas. These states arise due to variations in the characteristics of the particles that make up matter. Now, let's explore these states in more detail to understand their properties. Starting with the solid state, I want you to think about some common objects like a pen, a book, a needle, or a piece of wooden stick. If you sketch their shapes in your notebook, you'll notice they have a definite shape and boundaries and a fixed volume. Solids are rigid because they tend to maintain their shape when we apply outside forces. For example, if you hammer, pull, or drop a solid, it might break or change shape, but it's not easy to bend or compress them. Consider a rubber band. When you stretch it, it changes shape, but it can return to its original shape once you release the force. That's a key property of solids. Think about sugar or salt in jars. They take the shape of the jar but are still solid because their individual crystal structures remain fixed. Now, what about a sponge? It's a solid, but you can compress it because it has tiny holes filled with air, which can be expelled when pressed. All these examples show that solids have definite shapes, boundaries, and fixed volumes, and they are generally not easily compressible. They tend to resist shape changes, which makes them rigid, except when they break or are deformed under extreme force. Next, let's think about liquids. Imagine water, cooking oil, milk, juice, or a cold drink. If you pour these into different shaped containers, what do you notice? First, they do not have a fixed shape. They take the shape of the container. But they do have a fixed volume, which remains the same regardless of the container's shape. If you measure out 50 milliliters of any of these liquids and pour it into different containers, the volume stays the same, although the shape changes. Liquids flow easily from one container to another, which means they are not rigid and can change shape freely. These are called fluids. This flowing property is important because it allows liquids to diffuse into other substances, including gases in the atmosphere. For example, gases like oxygen dissolve in water, which is essential for aquatic life. This diffusion process allows aquatic animals and plants to breathe underwater, thanks to dissolved oxygen. So to summarize, solids have a fixed shape and volume, are rigid, and resist shape changes. Liquids, on the other hand, have a fixed volume but no fixed shape, and they flow easily, adapting to their container. Both states can diffuse into liquids, and this process is vital for life on Earth. Let's now talk about the gaseous state of matter. Have you ever seen a balloon seller filling many balloons from a single gas cylinder? Think about how many balloons he can fill from one cylinder and which gas might be inside it. This helps us understand how gases are used practically in daily life. Now, let's do a simple activity to better understand the properties of gases. Take 3 100 ml syringes and close their nozzles with rubber corks, just like in the diagram. Remove the pistons from all 3 syringes. Leave one syringe untouched, fill the second with water, and put pieces of chalk into the third. Then, insert the pistons back, and if needed, apply some Vaseline on the pistons for smooth movement. Try to push the pistons in each syringe to see what happens. What do you notice? The piston in the syringe with water is a bit harder to push, but in the one with chalk, it's even more difficult. In the empty syringe, pushing is easiest. This activity shows us that gases are highly compressible compared to solids and liquids. think about the LPG cylinders we use at home or oxygen cylinders in hospitals. These are compressed gases. CNG, or compressed natural gas, is also used as fuel in vehicles. Because gases are so compressible, large volumes can be stored in small cylinders and transported easily. Now, have you ever wondered how the smell of food reaches us from the kitchen? The aroma particles mix with air particles and spread through the air to our noses. Because gases diffuse so quickly, much faster than solids or liquids, this smell reaches us in seconds. This rapid diffusion is due to the high speed of gas particles and the large space between them. In the gaseous state, particles move randomly at high speed. This constant, random motion causes particles to collide with each other and with the walls of the container. The pressure exerted by a gas is a result of these collisions, each force exerted per unit area on the container walls. Finally, remember the activity with the syringes. Which one was easiest to push? That was the empty syringe, right? From this, we infer that gases are easily compressible because their particles are far apart and can be pushed closer together. And if you look at the schematic diagrams of the three states of matter, you'll see how particle motion differs in solids, liquids, and gases. In gases, the particles move freely and randomly, which is a key point in understanding their unique properties and behavior. Let's start with the activity. Take about 150 grams of ice in a beaker and suspend a laboratory thermometer so that its bulb touches the ice, just like in the diagram. This helps us see how temperature affects the ice. Now moving on to the questions. First, the concept of density. It's the mass per unit volume of a substance. Think of it as how tightly packed the particles are. For example, if we arrange air, chimney exhaust, honey, water, chalk, cotton, and iron in order of increasing density, we see that air is the least dense and iron is the most dense. Let's look at the differences in the characteristics of the states of matter. Solids have a fixed shape and volume, are rigid, and particles are tightly packed. Liquids have a fixed volume but take the shape of their container, are fluid, and particles are less tightly packed. Gases fill the entire container, are compressible, and particles are widely spaced. Now about some key observations. A gas fills the entire vessel it's in because particles move freely and spread out. Gases exert pressure on the container walls because their particles are constantly moving and hitting the walls. A wooden table is called a solid because it has a fixed shape and resists shape changes. Also, we can move our hand easily through air, which is a gas, but moving through a solid like wood requires force, like a karate expert. Next, let's talk about density again. Liquids generally have lower density than solids, but ice floats on water because of a unique property. When water freezes into ice, its particles arrange in a way that makes ice less dense than liquid water. That's why ice floats. Finally, let's revisit the idea of matter changing its state. Water can exist as ice, water, or water vapor. During these changes, particles either come closer together or move further apart. When ice melts, particles gain energy and spread out into water. When water boils, particles gain enough energy to become vapor and escape into the air. These processes show us how matter transitions from one state to another based on energy changes. And that's how the particles inside matter behave during these state changes, helping us understand the nature of matter much better. Let's begin by starting to heat the beaker on a low flame. As you do this, pay close attention to the temperature when the ice begins to melt. This is the point where the solid ice turns into liquid water. Next, continue heating until all the ice has fully converted into water, and note that temperature as well. It's important to record these observations because they help us understand the process of solid turning into liquid, which we call melting. Now take a glass rod and put it in the beaker. Keep heating the water while stirring gently. Watch the thermometer carefully as the water starts boiling. Continue observing until most of the water has vaporized and record that temperature. This process shows the transition from the liquid state to the gaseous state or vapor. When we increase the temperature of solids, the particles gain more kinetic energy, meaning they vibrate faster. Eventually, this energy overcomes the forces holding the particles together, causing them to leave their fixed positions. This is what happens during melting. the solid becomes a liquid. The specific temperature at which this occurs at atmospheric pressure is called the melting point. For ice, this melting point is 273.15 Kelvin, or 0 degrees Celsius. The melting point also indicates the strength of the forces between particles. The process of melting, or fusion, involves heat energy being used to break these forces. Interestingly, during melting, the temperature remains constant even though heat continues to be supplied. This is because the heat energy is used up overcoming attraction forces, not increasing temperature. We call this energy the latent heat of fusion, which is essentially the hidden heat required to change a solid into a liquid at its melting point. In the case of water at 0 degrees Celsius, the particles have more energy than in ice at the same temperature because some of that energy is used in the phase change. When we keep supplying heat to water, the particles move even faster until they have enough energy to escape the liquid's attraction forces, leading to boiling. The temperature at which this happens at atmospheric pressure is called the boiling point. In water, it is 373 Kelvin, or 100 degrees Celsius. This brings us to the concept of latent heat of vaporization, which is the energy needed for water to turn into vapor at its boiling point. Just like the latent heat of fusion, this energy is absorbed without changing the temperature, but is used to overcome the forces holding the particles together in the liquid state. Remember, particles in steam at 373 Kelvin have even more energy than particles in liquid water at the same temperature. That's because they've absorbed extra energy in the form of latent heat of vaporization. So overall, we see that matter can change from one state to another by simply changing the temperature and supplying or removing heat energy. This fundamental principle helps us understand the behavior of substances around us, how they melt, boil, and transform from solids to liquids and gases. Let's explore what happens when a substance is enclosed in a cylinder. Do you think the particles come closer? Yes, they do. Increasing the pressure pushes the particles closer together, and decreasing the pressure allows them to move apart. This change in pressure can actually alter the state of matter, solid, liquid, or gas. Some substances, like camphor, change directly from solid to gaseous state and vice versa without becoming a liquid first. This process is called sublimation when going from solid to gas, and deposition when going from gas back to solid. Now I want to take you through an activity to help understand this better. Take some camphor, crush it, and place it in a china dish. Then, put an inverted funnel over the dish and place a cotton plug on the stem of the funnel, like in the diagram. Here's an interesting point. Atmospheric pressure, which is measured in units called atmospheres, plays a crucial role here. 1 atmosphere equals 1.01 times 10 to the 5 pascals. At sea level, the atmospheric pressure is considered as 1 atmosphere, or normal atmospheric pressure. When you apply pressure and reduce the temperature, gases can be liquefied. For example, solid carbon dioxide, or dry ice, is stored under high pressure. When the pressure decreases to 1 atmosphere, it doesn't turn into a liquid but directly becomes a gas. That's why we call it dry ice, because it sublimates directly from solid to gas. So overall, we can see that both pressure and temperature are key factors in determining whether a substance is solid, liquid, or gas. Now let's heat the setup slowly and observe what happens. From this activity, what can you infer? You'll notice that some substances can skip the liquid stage entirely when changing states. That's sublimation. Conversely, gas can turn directly into a solid through deposition. Understanding the effect of pressure is essential. When we increase pressure on a gas, the particles are forced closer together. This change in the distance between particles affects the state of the matter, as shown in the diagram of the interconversion of the 3 states. In summary, both pressure and temperature work together to influence the state of a substance, and these changes are fundamental to understanding the behavior of matter in different conditions. Now, let's look at some key observations about evaporation. When we reprint the data from 2025-26, we see that recording room temperature and noting the time or days taken for evaporation helps us understand how different conditions affect the process. It's important to repeat these activities on a rainy day and compare the observations. So, what can we infer about the effect of temperature, surface area, and wind velocity on evaporation? Well, we observe that the rate of evaporation increases with an increase in surface area. Since evaporation is a surface phenomenon, spreading out clothes to dry them speeds up the process. Next, increasing temperature also increases evaporation because higher temperatures give particles more kinetic energy, enabling more to escape into the vapor state. Conversely, humidity plays a role too. When the air already contains a lot of water vapor, it can't hold much more, so evaporation slows down. And what about wind speed? We notice that clothes dry faster on windy days because the wind moves water vapor particles away from the surface, reducing the vapor pressure around the liquid and speeding up evaporation. Now let's connect this to cooling. When evaporation occurs in an open vessel, the liquid particles absorb energy from the surroundings to escape into vapor. This energy absorption causes the surroundings to cool down, which is why evaporation causes a cooling effect. Moving on to temperature conversions. If I ask you to convert 300 Kelvin to Celsius, you subtract 273, giving 27 degrees C. For 573 Kelvin, it's 300 degrees C. At 250 degrees C, water exists in the gaseous state, while at 100 degrees C, water is in the liquid state. The interesting thing is, during a change of state, like boiling or melting, the temperature remains constant because all the energy supplied is used for changing the state, not increasing temperature. To liquefy atmospheric gases, one method is to compress and cool them until they turn into liquids. This is how gases like oxygen and nitrogen are stored. Now, do we always need heat or pressure to change states? Not necessarily. For example, water evaporates slowly at room temperature without boiling, and wet clothes dry without reaching boiling point. Particles in matter are always moving, with different kinetic energies. In liquids, a small number of surface particles with higher energy escape as vapor. This process is called evaporation. It can happen at temperatures below the boiling point. Let's understand this better through an activity. Take 5 ml of water in a test tube near a window or under a fan, and compare it with 5 ml of water in an open dish near a fan, and another 5 ml inside a cupboard or on a shelf. Notice how evaporation varies in these different conditions. Today, we will reflect on what we have learned about matter and its behavior. First, we understand that matter is made up of tiny particles, which are too small to see individually. These particles exist in 3 states: solid, liquid, and gas. The forces of attraction between these particles vary in strength, being strongest in solids, intermediate in liquids, and weakest in gases. This variation explains many of their properties. We also learned that the spaces between particles and their kinetic energy differ across these states. In solids, the particles are closely packed with minimal space and low energy. In liquids, the particles are a bit farther apart with moderate energy, and in gases, they are spread out with the highest energy. Let's consider what happens when you pour acetone, like nail polish remover, on your palm. The particles in acetone gain energy from your skin or the surroundings and start to evaporate. This process absorbs heat from your palm, making it feel cool. Similarly, after a hot day, sprinkling water on roofs or open grounds helps cool the surface because of water's high latent heat of vaporization. It absorbs a lot of heat as it evaporates. Can you think of other everyday examples where evaporation causes cooling? For instance, when we sweat, our body cools down as the moisture on our skin evaporates. This natural mechanism helps regulate our temperature, especially during hot weather. Why do we wear cotton clothes in summer? Cotton is very good at absorbing sweat. When sweat is exposed to the air, it evaporates easily, which helps keep our body cool. This is why breathable, natural fabrics like cotton are preferred in hot weather. They facilitate evaporation and help us stay comfortable. Now, why do we see water droplets on the outside of a glass filled with ice-cold water? When warm, moist air comes into contact with the cold surface of the glass, the water vapor in the air loses energy and condenses into tiny droplets of water on the glass surface. This is a clear example of condensation happening because of temperature differences. Moving on to some questions. Why does a desert cooler work better on a hot, dry day? Because in dry air, the rate of evaporation is higher, so the cooling effect is more pronounced. Similarly, how does water in an earthen pot become cool in summer? The porous nature of the clay allows some water to evaporate, which cools the remaining water inside, thanks to the process of evaporation and the properties of the material. Why do our palms feel cold when we put acetone, petrol, or perfume on them? Because these substances evaporate quickly, absorbing heat from our skin during evaporation, which makes our skin feel cool. And why can we sip hot tea or milk faster from a saucer than from a cup? The larger surface area of the saucer allows heat to escape more rapidly, speeding up cooling and making it easier to sip. Finally, what kind of clothes should we wear in summer? Light, breathable fabrics like cotton are ideal because they absorb sweat and promote evaporation, helping us stay cool and comfortable during the hot months. Let's talk about matter in our surroundings. The arrangement of particles is most ordered in solids, which means particles are tightly packed in a regular pattern. In liquids, these layers can slip and slide over each other, making them less ordered. For gases, there is basically no order at all. Particles move randomly and freely. Now, it's important to remember that the states of matter are interconvertible. We can change one state to another by adjusting temperature or pressure. For example, sublimation is when a solid changes directly into a gas without becoming a liquid first. Conversely, deposition is when a gas turns directly into a solid without passing through the liquid phase. Moving on to boiling and evaporation. These are both ways that liquids turn into vapor, but they happen differently. Boiling is a bulk phenomenon, meaning particles throughout the entire liquid change into vapor at once. Evaporation, on the other hand, is a surface phenomenon. Only particles at the surface gain enough energy to overcome the forces holding them in the liquid and escape into the air. The rate of evaporation depends on several factors: the surface area exposed, the temperature, humidity, and wind speed. And interestingly, evaporation causes cooling because energy is used to convert liquid into vapor. Now, let's touch on some key energy concepts. The latent heat of vaporization is the energy needed to turn 1 kilogram of a liquid into gas at its boiling point, at atmospheric pressure. Similarly, the latent heat of fusion is the energy required to change 1 kilogram of solid into liquid at its melting point. Finally, here are some measurable quantities and their units that are useful to remember. Temperature is measured in Kelvin, symbol K, length in meters, m, mass in kilograms, kg, weight in newtons, n, volume in cubic meters, m3, density in kilograms per cubic meter, kg/m3, and pressure in pascals, pa. Understanding these concepts helps us grasp how matter behaves in different states and conditions around us. Let's start with the first set of questions about temperature conversions. When converting from Kelvin to Celsius, remember that Celsius equals Kelvin minus 273. So, for 293 Kelvin, subtract 273 and you get 20 degrees Celsius. Similarly, for 470 Kelvin, subtract 273 and you get 197 degrees Celsius. Now, converting Celsius to Kelvin is straightforward. Add 273 to the Celsius temperature. For example, 25 degrees Celsius becomes 298 Kelvin, and 373 degrees Celsius becomes 646 Kelvin. Moving on to observations about naphthalene balls. They disappear over time without leaving any solid behind because they sublim, meaning they transition directly from solid to gas. This is why you notice the balls gradually vanishing. Next, the reason we can smell perfume from several meters away is due to the volatile nature of perfume molecules. They evaporate into the air and spread out, allowing us to detect the scent even from a distance. When arranging substances like water, sugar, and oxygen based on the forces of attraction between particles, oxygen has the weakest forces, followed by water, which has moderate forces, and sugar has the strongest because it's a large molecule with many attractive forces within. Considering the physical states of water at different temperatures. At 25 degrees Celsius, water is a liquid. At 0 degrees Celsius, it's at the freezing point, so it can be ice or water depending on conditions. And at 100 degrees Celsius, water boils and turns into vapor. Water remains a liquid at room temperature because of its unique hydrogen bonding, which keeps the molecules loosely connected, but still fluid. An iron almira remains a solid at room temperature because metals have strong metallic bonds, which require a lot of energy to break. Now, why is ice at 273 Kelvin more effective in cooling than water at the same temperature? Because ice absorbs more heat as it melts, providing a cooling effect for longer. Also, it remains solid and maintains contact with what it's cooling. Regarding burns, boiling water produces more severe burns than steam because when steam condenses on skin, it releases a lot of heat, causing more damage. Finally, about the diagram showing the change in state, A could be solid, B is melting to become liquid, C is liquid, D is boiling to become gas, E is gas, and F is condensation back to liquid. This cycle illustrates the states of matter and phase changes clearly. Now, let's move on to a fun group activity that will help us understand how particles move in solids, liquids, and gases. You'll be preparing a simple model to demonstrate these different states of matter. Here's what you'll need: a transparent jar, a big rubber balloon or a stretchable rubber sheet, a string, and some chickpeas, black gram, or dry green peas. To make the model first, put the seeds into the jar. These seeds will act as the particles. Next, sew the string to the center of the rubber sheet and secure it with tape to keep it tied tightly. Then, stretch the rubber sheet over the mouth of the jar and tie it securely. Once your model is ready, you can run your fingers up and down the string. Start gently and then try tugging it more rapidly. This movement will help us observe how particles behave in different states, how they vibrate in solids, slide past each other in liquids, and move freely in gases. This activity is a visual and hands-on way to understand the concept of particle movement and phase changes, like from solid to liquid or liquid to gas. It connects directly to the overall theme of matter in our surroundings, showing us how matter changes state and behaves in different environments. So, give it a try, and let's see how well you can demonstrate these fascinating changes.